given you the rights to record.
I'm recording right now.
Okay, great. Okay, so yeah, no problem with the recording. Who's talking? Okay, great. No problem. So yeah, we're page, where is it? 94 roughly in your notes. I'm just taking a look at the end of the theory. So the first thing that we're going to review is the absolute value function that you'll come across again and again in the next year. So hopefully it's a function that you've seen before. It's defined like this. So the absolute value function is defined on R. It's equal to, so you take the absolute value of x, that's equal to x for x that's positive, and it's equal to minus x when x is negative. One thing that we can note is that there's an alternative expression. You can also write the absolute value function as follows. So absolute value of x, it's also equal to the square root of the square of x. So this first sort of definition is the proper definition in the sense that that's how the function is sort of really defined. It gives you the sort of positive, it gives you a positive value equal to either x or minus x, depending on where you are on the real line. And this is an expression that's equal to the absolute value function that's sometimes easier when manipulating it. So that's the definition. And if you take a look at your notes, there are certain things that are mentioned that are relevant. So it's defined on R, okay? It's continuous on R. One thing that's really important is that it's only differentiable on R star, okay? It's not differentiable at 0. That's really important to keep in mind. You can't differentiate the absolute value function at 0. And this function is a really important function in analysis. So we saw it when using limits. I think we saw it a little bit possibly in this chapter. And we often have manipulated things called triangular inequalities. So what are the triangular inequalities? They're things that we've already come across. And they're these two equalities. So the first one tells you that the square root of x plus, not the square root, the absolute value of x plus y is smaller than the absolute value of x plus the absolute value of y. This inequality is very closely related to the Pythagoras theorem. If you take a look at what this means geometrically, you'll find that the equality case of the triangular inequality is very much related to Pythagoras. And I think this is one that the second one is one that we've proven in some tutorial exercises, I think. I think it was in chapter 5, we proved this from what I remember in a specific setting. So these two inequalities you'll come across quite a lot, and they allow you to upper bound and lower bound the sum of the absolute value of the sum of two values. And so one thing to note is that when manipulating the absolute value function, you've got to be really quite careful. So care should be taken when manipulating the absolute value function. So we'll give a couple of examples of, or three actually, of how you need to be careful. Now, the first example is if you're asked to solve some equations. So let me give an example of tricky situations. First one, solve x Okay, imagine you want to solve this first equation for x on R. So the absolute value of x minus 12 needs to be greater than minus 1. How would you go about solving this inequality?
We could do it geometrically.
Yeah, how would you do that?
We have a range from minus 12 to 12 around minus 1, and x can be there.
Okay. So I think I see what you mean. So that involves basically doing a whole load of manipulations. Yeah. Is there anything else that that's easier that allows us to solve an equation, or this equation in particular?
We could replace the absolute value with the square root of the square of x minus 12. And
yeah.
Yes.
Yeah, we can do that. You can absolutely do that. Is there anything else? Just to give you an idea, this was a question in some of the past Ultimat exams, and it generally does catch people out. There's something really, really simple to say here. Do you know anything about this?
Just take the two equation. I mean
Yeah.
minus x plus 12 is greater than minus 1 if x is smaller than 12, and x minus 12 is greater than minus 1 if x is bigger than 12.
Yeah, that's how you do it in general when there's an absolute value and a constant. Can you tell me anything about the sign of the absolute value function?
It's always true, actually.
Yeah, exactly. Yeah, this is an example of an equation where you can very quickly try and solve it using various methods, but it's actually always true. For any x in R, x minus 12, sorry, is greater than 0. So the above equation holds on R. Okay, so all of the methods that you mentioned probably work in general when you've got a constant, but do take care when you've got a constant, because in many cases you, or in some specific cases rather, you can just solve the equation directly because, for example, you're greater than something that's negative, so that's always true. Another example is having to solve this. So you're in a setting where you've got absolute values on the left-hand side, absolute values on the right-hand side. How would you go across solving this equation? There's no trick here like this one. I mean, there's no sort of trivial answer here. It's more, in this case, yeah, you can. That's a really good approach to do. The way that you can get caught out is to want to try and give 4 cases. So a case where x minus 2 positive, x minus 2 negative, 2x positive, 2x negative. And if you do that, you risk getting completely messed up in between all the different cases. But you can write the following. If I do it slowly, I'm using the definition of this, not the definition of the square root, but the equality that was above. And that's not an equals, that's a greater than. Okay, but that can then be lifted to 2x squared. To the equation without the square root. So in fact, when you're actually performing these type of operations, you can directly go from this to this. And here you see on the right hand side, you've got 4x squared. And so you end up with a polynomial type equation. So if we expand the left-hand side, you get x squared minus 2x plus 4 greater than 4x squared. So this can then be tackled.
Sorry, is it minus 2x squared? X squared
What?
minus 2x or minus 4x?
Whereabouts?
I mean, x minus 2 squared.
Yeah.
Or maybe I'm wrong.
You mean from there to there?
No, I think he meant that it's x squared minus 4x plus 4 because it's like the. It's
Oh,
the
you
egg
mean
one.
to simplify this expression? Is that what you mean? Perhaps.
No, third line, you have x squared minus 2x. It should be x squared minus 4x.
Oh, yeah, thank you. Yeah, okay, that's out there. Thanks. Yeah, that's absolutely true. And yeah, once you get to this stage, this can be tackled using analysis of the underlying polynomial. So you can write this eventually as a polynomial greater than 0, for example. You can compute the roots of that polynomial if it has any, and basically work out on which range of R this equality holds, or inequality holds rather. So there are many sort of examples of cases where you've got to be careful with the square roots inequality. Most of the time, you're basically better off by somehow getting rid of the square root, not the square root, the absolute value. So here we got rid of the absolute value by using the square root in the sort of square expression. But sometimes you can also use this. So that's an alternative way, no, not that, of rewriting the square root. In this case, rather than replace the absolute value, by the square root of the thing squared, if you end up with any inequalities like this, so absolute value of x smaller than m, you can also rewrite it as minus m smaller than x smaller than m. And then you've got to be careful in that you've got two possibilities. Too often, basically, with the square root, the absolute value function, we often end up seeing only one of these two possibilities when there are two. So you've got to be really careful with these types of equations. So this is a final example. So x absolute value is smaller than m, x in R. What that gives you is this result here. Okay, so further on in your notes, after the sort of mention of all the different inequalities and the sort of alternative notation for the absolute value, there's the proof of the triangular inequality. Okay, so the proof is in your notes, and it's actually proven in the complex case. It's actually used more in the complex case. I think it makes more geometrical sense in the complex case. So you can note that the triangular inequalities extend to C as follows. So the proposition in your notes tells us the following. It tells you that for Z1, Z2, and C, if you replace the absolute value by the modulus of a complex number, you have both the lower triangular inequality and the upper triangular inequality. So you can basically bound the modulus of Z1 plus Z2 between two other terms. And how we prove this is as follows. So I don't know if you remember this, but the modulus squared of a complex number is equal to the complex number times the conjugate. So that's what's used here. And if you then expand the expression, so you just expand this, you get the following 3 terms. And so what we want to do is use this approach to prove the first inequality here, where we prove the upper sort of bound. And so what we want to do that is to prove that this is somehow smaller than, I think, this plus this squared, probably. And so what we need to do is manipulate this term and sort of say something about it that we can deal with. And what we can say is that the real part, this is the real part of Z1, Z2 bar, so that's a real part of a complex number. If you take its modulus, it will be smaller than the modulus of the full complex number. Okay, if you want to see that perhaps a little bit more, if we let x in C, x equal to A plus IB, then the modulus of the real part of x is equal to basically the absolute value of A, and the modulus of x is equal to the square root of A squared plus B squared. Okay, so if we rewrite perhaps the term that's above by absolute value of A squared, then you see that this is always smaller than that because B squared is positive. So that's what's written here. And then you can rewrite the complex number that's in the real part. As it's a product, the modulus of a product, you get the product of the modulus terms, and then you use the fact that the modulus of the conjugate is equal to the modulus of the initial number. So you get this absolute value for this term, and you can inject it here. And so you get Z1 plus Z2 squared, smaller than Z1 squared, Z2 squared with the moduluses, plus 2 times this product. And if you look at what that is now, that's a square. Okay, that's modulus of Z1 plus modulus of Z2 squared. Okay, and if you apply the square root, you get exactly this inequality here. And to prove the second property, you can do it in a way that we've done in a tutorial exercise. So if you want to prove this one, you first consider Z1, and you can write Z1 as Z1 plus Z2 minus Z2. And if you apply the first triangular inequality, calling this perhaps a capital Z1 and this a capital Z2, you can use this then, and you can apply the first triangular inequality to reach these 2 terms, and it proves the sort of lower triangular inequality. Okay, so that's how you can prove it in the complex space, and as it works in the sort of complex setting, then in particular it works on the real line, and the modulus on the real line becomes the absolute value. One thing that you can note is that the first triangular inequality, so this one, has quite clear geometrical interpretation. Basically, if you take a triangle, if you take a triangle and you look at the longest side, so this one, the length of this side is always shorter than that plus that. And so if you put yourself into a, for example, complex plane, this is a vector. You can compute, I suppose, the length of this vector and the length of these 2 vectors, and this property basically holds. So the first one has sort of geometrical interpretation. I'm not sure about the interpretation of that one, but it's a useful property as well. Okay, so that's a little note on the absolute value function. What you need to take away from it is that you need to just be careful when dealing with the absolute value function. Now, if you look in your notes, on page 95, I think you've got a couple of inequalities that you'll definitely hear about throughout the next few years, but we're not going to cover them now. Cauchy-Schwarz and Young's inequality. they're in your notes if you ever want some references, but we're not going to discuss them now. What we are going to discuss is the idea of convexity, because that's a useful property for functions. So let's just take a look at what that means, and that will finish off the chapter 6's sort of theory. Okay, so convexity is a notion that will help us with the analysis of functions going forward. So it's something that's really useful in mathematics, and we can take a look at the definition of it on the real line. So what we're going to take is a function f mapping from some interval of r, so it can be r itself, but also a smaller interval, to r. And it's convex if the following properties hold. So it's if and only if the following statement holds. If you take any 2 points on your interval, the value at your function at a certain point, which is quite strange, it's t of x plus 1 minus t of y, is smaller than t times f of x plus 1 minus t f of y. Now, the easiest way to see what this means, because it's quite a visual property, is to have a look at the graph of functions. So I'm going to draw a function that behaves like this. I'm going to place a point x here and a point y here. So this is the curve of a certain function. Okay. Now, where is the sort of point tx plus 1 minus ty if you take t between 0 and 1?
Between x and y.
Yeah, absolutely. So if you set t equal to 0, you're going to start at y, so here, and as y increases, you're going to head towards x. This is called a convex combination of x and y. So we're basically looking for any t between 0 and 1, the value of the function itself at that point, so the value of the function on this sort of interval, and we're comparing it to a certain combination of f of x, which is here, and f of y, which is here. And so no matter where you are along the point, sort of along this interval, your function will be convex, if and only if, as you go along, when you compare the value of the function, for example, at this point, that may be for t equal to, I don't know, 0.1, you've got to be smaller than 0.1 times f of x plus 0.9 times f of y. Now, that's quite difficult to see with the definition as it is, and it's actually quite difficult to prove for functions in general under this statement. So you've got this nicer proposition that tells us what convexity means. That's wrong, actually, is it? No, that's okay. So if you're differentiable, if you're in the case where your function is differentiable, you'll be convex if and only if the derivative of your function is non-decreasing. And if you're 2 times differentiable, which is often the way that the statement's given, you'll be convex if and only if your second derivative is positive. Okay, second derivative positive implies f prime is non-decreasing. So those are 2 ways of proving it. And this is the best sort of statement to actually see what it means. Does this, if we take a look at the term on the right hand side, so we're going to compare f of y to this value here, f of x plus f prime of x, y minus x. Does this sort of thing remind you of anything?
It's the tangent at point x.
Yeah, yeah, I think it is. Let me just take a look. Yeah, the convexity of a function is directly linked to the behavior of some of its tangents. So if we take a look at the function that's drawn below, I can tell you that this function, just by the way it looks, it's convex. Okay, and one thing that's important is that it's always above all of its tangents. That's what this means here. So if we draw all the tangents to the function below, so for example, this is a tangent to at a certain point, this as well, this as well. There's sort of a kink here due to the fact that I haven't drawn it very well, but imagine that it's much smoother. Basically, the function's always above all of its tangents, and that's what this inequality sort of models. So x squared, for example, is convex. X to the power 4 is convex as well. The exponential function is convex. A lot of the functions that you know have convexity properties. So what you can take away geometrically a function is convex on an interval if it is above all of its tangents on the interval. So for any xy at I, if you take a look at the value of f at y, you have f of y greater than f of x plus f prime of x, y minus x. I think that's what's written, yeah. So that gives you an interpretation of what it means. And remembering that it means that the second derivative is positive is good, because then that allows us to compute sort of, or prove that a function is convex. You've got the opposite behavior when this inequality holds as the other way around. So f of tx plus 1 minus ty is greater than the terms on the right hand side. Your function is said to be concave. And so when you're concave, it means that f prime is non-increasing. This thing holds with the other inequality, and f prime prime is negative. And one thing that you can take away about being concave is that f is concave on I if and only if minus f is convex. Okay, and here we've got the example of a convex function. So you can probably wonder why this is useful. One of the reasons why it's useful that you'll probably see later on is that you can say a lot about the minimums and the maximums of a function if you know that it's convex or concave. The other thing that's nice is that if you know that a function is, for example, convex, okay, so you have a function that's twice differentiable, you compute the second derivative and you show that it's always positive, then you know that the function is above all of its tangents. And so whenever you compute a tangent to the function and you want to know how to graph it, you know that the function will be above it and you don't have to individually study the relative positions. So that's one thing that you can take away from convexity of functions. And that's the last sort of theory thing we're going to see for chapter 6. Are there any questions on the couple of points that we've just seen?
No, don't really.
Okay.
How will it be asked if a function is concave or convex? Will they just ask their convexity, or when we're asked to analyze a function, do we also have to do that now? Or
Oh, that's a really good question. So the first thing is that in general, if you're in a sort of a test type setting and you're asked to analyze a function, like we've been doing recently, generally a lot of the sort of intermediary steps are detailed. Because there are a lot of steps that we've been doing, like, for example, computing the derivative, computing the differentiability domain, the derivative, looking at tangents. The steps will sort of be given, and one of those steps will generally be show that such and such a function is convex, and it will be then useful when computing the relative position of tangents, for example. So it would be explicitly asked, I guess, of you if you need to use it. And the important thing to take away, I guess, is you need to have seen these definitions before, but you need to remember that f prime prime positive is means that your function is convex, and then the fact that a convex function is always above its tangents. So one function that you can remember is basically x squared. X maps to x squared is convex on R. You know that the second derivative of this function is 2. So if you're ever in doubt and you know that x squared is convex, then that will give you that the second derivative has to be positive, and you can guess by the sort of form of the curve of x squared that it's going to be above its tangents. Does that answer the question a little?
Yes, yes, it does. Thank you.
Okay. So what we can do, if you're okay with these two sort of notions, is turn to taking a look at some exercises. So I think that I'm not sure that we'll apply all of these things straight away today. Let's see. Because the exercises that we've got at the moment are mostly related to either the hyperbolic trig functions. So we've got exercise 4 to do. We've got stuff related to power functions. There isn't much, for example, related to convexity and things yet, but it will definitely come up at various points. And if you take a look at past papers, you'll see that I think it's quite explicitly asked of you at some point. So what we can do is take a look at exercise 4. I don't think we've done exercise 4 yet. And try and correct that exercise. So it's this one, and it's the last exercise on hyperbolic trig functions. And we're actually going to sort of manipulate the different properties that we've proven. So if you take a look at the exercise, it's all based on a certain equation related to hyperbolic trig functions. And the equation does look possibly a little intimidating to start with. So we want to find the values of x such that this is satisfied, or rather such that this is satisfied. So g of x equal to 0 and then g of x negative. So maybe we can get started with the first question. So we want to find x in R such that g of x equal to 0. Okay, that's the sort of thing that we want to do in this question. Maybe we can write what it means for g of x to be equal to 0. So if we just copy out a function g of x, we reach this. So hyperbolic sine squared minus 2 hyperbolic cosine equal to 0. Do you have any idea how we can proceed when we get to that step?
We know that hyperbolic sine square minus hyperbolic cosine square is equal to 1. So we can express hyperbolic sine in function with hyperbolic cosine?
Yeah, absolutely. So you know that we know if I write it on a corner of the sort of notes, you know that CH squared minus SH squared, that's equal to 1. Okay, so what that tells us is that basically SH squared is going to be, let me get this right, CH squared minus 1. So CH squared of x minus 1 minus 2CH of x is equal to 0. You can sort of justify, perhaps put the thing that I've written above down here instead. So that's a really good thing to do. Okay, maybe if I just reorder the terms here, you end up with this equation. Okay, CH squared minus 2CH minus 1 equal to 0. Now, is there any way you'd want to proceed when you reach this?
We can solve it as a polynomial, saying that CH is x.
Absolutely, yeah. So the idea here is that if you didn't have CH but had, for example, x instead, you'd be really quite happy because it's just finding the roots of a polynomial. So we're going to do that. We're going to do that and set. We set, for example, y maybe equal to CH of x. Okay, and reach y squared minus 2y minus 1 equal to 0. One thing that is important to note is that we can do this sort of operation as hyperbolic cosine is basically inversible. It's I think it's a bijective function, so it doesn't really matter whether you find a value for CH of x or x. You can always pop from one to the other without any problems. So if we have this polynomial, we can compute its roots, as we've done many times this year. So let's have a look. We'll probably have delta equal to 4 plus 4. So that's 8, and that's 2 square root of 2 squared. Okay, you get 4 times, basically it's 4 times 2, and that gives you 2 square root of 2 squared. And so if you compute the roots, two real roots. Okay, if you compute them, you get 1 plus square root of 2 and 1 minus square root of 2. Okay. So now we want to revert to the hyperbolic cosine values, or compute, I suppose, x instead of y. Okay, so we need to find a way of reversing everything. So what we can do is say that y squared minus 2y minus 1 equal to 0. That's equivalent to y equal to 1 plus square root of 2, or y equal to 1 minus square root of 2. We now want to put back to the hyperbolic cosine and find values for x. Now, one important property that we prove for the hyperbolic cosine is relative to the values that a hyperbolic cosine can take. I don't know if you remember.
Hyperbolic cosine is greater than 1.
Exactly. So hyperbolic cosine is greater than 1. For any x in R, CH of x is greater than 1. So what does that mean for the two values that we found for y here?
Only the first one is possible.
Yeah, exactly. So the solutions if I can just denote this solution, this equation R, the solution with an S possibly, because there may be several, the solutions 2 star satisfy. Actually, I said something that I shouldn't have said earlier. It's not an invertible function at all. It's invertible on R plus and it's invertible on R minus. Anyway, they satisfy CH of X equal to 1 plus square root of 2. If your function had been invertible, we wouldn't have had this problem, I don't think. Okay, so we've sort of reduced our problem somewhat, I guess. We've started out with an equation with hyperbolic trig functions. Okay, we've written the related polynomial, replacing y by ch of x. The related polynomial has 2 roots, 1 plus square root of 2, 1 minus square root of 2, and only one of these roots is possible. But if we take a look at the graph roughly of ch of x, it's not at all invertible. And what you can see is that 1 plus square root of 2 could possibly be around here, and we're going to have 2 values that we need to compute that will give us 1 plus square root of 2 through the mapping ch of x. So how are we going to do that? There's possibly several ways of doing it, but the easiest way is possibly to replace ch of x by its expression now. So can you remember the expression for the hyperbolic cosine?
Exponential of x plus exponential of minus x divided by 2.
Yeah, exactly. What am I doing? So ch of x equal to 1 plus square root of 2. That's equivalent to exponential x plus exponential minus x. If I get rid of the 2 and multiply on the right hand side, you'll get this. Now, this should ring some bells related to an equation that we've already dealt with. How would you solve this equation here?
Apply a ln to both sides.
Are you sure? Would that work? Yeah, actually, it might work. There's another way of doing it, because I'm not sure how you deal with exponential of x plus exponential minus x with the ln.
Exponential, you have ln of a plus b, so it's ln of a times ln of b. So you have x times minus x, so minus x squared.
Yeah, actually, yeah, no, yeah, okay, yeah, that should work. There's another way of doing it that will allow us to revise polynomials. And your method is completely, probably completely right. There's another way.
Multiply by e to the x?
Yeah, absolutely. So if you multiply by e to the x, you get e to x plus 1 equal to 2 times 1 plus square root of 2 e to the x. Okay. And if we just reorder this equation, we get e to 2x minus the exponential x term. Okay. And then we can deal with this for another polynomial. So if we set x equal to e to the x, we want to solve the following. X squared minus 2, 1 plus square root of 2x plus 1 equal to 0. And if we look at that one, we've got delta again. So delta is equal to 4 times 1 plus square root of 2 minus 4. That's positive. And that's equal to 4 times square root of 2, actually. And I don't know if we can write that as...
Isn't there a square 4 times 1 plus square root of 2 squared?
Yeah, I think you're absolutely right. Yeah, sorry. yeah, and it's still positive, and so there are more terms than the ones I'd written. So we got, if we expand the square, we get 4. We get plus 8 square root of 2 plus probably 8. Is that right? Minus 4. Okay, and we can probably reduce this expression slightly further. So hopefully, yeah, we'll get 4. We get something that's a bit of a pain to deal with, but we get this. Okay, so we get 2 possibilities. We get minus b minus square root of delta divided by 2a, or the sort of the one where we take the other sign. So we get 1 plus square root of 2, and we get plus or minus the square root of this thing simplified by 2, so 4 basically disappears, and we've got square root of this term. Okay, so it's either 1 plus square root of 2 plus square root of 2 plus 2 square root of 2, or the thing with the minus sign. Okay, and then how can you reach the solutions once you get this?
We take ln of that.
Yeah, absolutely. One thing that we can check is that both of these solutions are positive. Okay, one of them is trivial, or rather it's trivial to see that it's positive. We can check that 1 plus square root of 2 minus square root of 2 plus 2 square root of 2 is positive. Okay. It's important only to check this sort of thing before computing the logarithms. Here there's something funny that happens, which means that it's quite easy to see. If we take 1 plus square root of 2 squared, okay, you'll have 1 plus 2 square root of 2 plus square root of 2 squared, so 2. So that's 3 plus 2 square root of 2, okay, which will be strictly bigger than 2 plus 2 square root of 2. And if you look at what that means, if you now take the square root of both the terms, yet square root of 1 plus square root of 2 squared bigger than 2 plus 2 square root of 2 with the square root on it. This here is equal to the term that's here, and that one is equal to the term that's on the right hand side. So we get the right sort of sign for both of the terms. The second one's got a plus in between, so you can easily check that it's positive. We finally obtain 2 solutions.
I have a question.
Yeah.
We know that the hyperbolic cosine is pair.
Yeah.
Can we just take one of these 2 solutions and solve it, and just say that the second one has to be on the minus the first one?
Yeah, I think that does absolutely work. It should do. Yeah, that should. And if we apply the logarithm here, you can express the 2 solutions like this. So one is logarithm of 1 plus square root of 2 plus this extra term, and the other one is the same thing with the minus sign between the 2. And to either mention that you could probably apply the logarithm directly from here. Yeah, I think that would save some of this reasoning, and hopefully you'd reach the same solutions. So you get minus 2x squared equal to a logarithm. And then you'd have to deal with the square root of a logarithm. So that's possibly slightly hard. But yeah. That gives us the 2 solutions to the equation. You can see that they're not the nice system solutions, and there's a little bit of work needed to reach them. So if I don't know if you've finished or if you're writing or anything. If you look at question 2, we're going to sort of build on this to get the sign of the sort of the behavior of the function now. Okay, are you writing or have you finished?
Still writing. Sorry.
Okay, no problem.
Okay, it's all good. Thank you.
Okay.
For me anyway. I don't know about.
Yeah, no problem. If anyone else is still writing, do speak up, because if not, we can continue working on this exercise. Actually, I'll just get the question and then I'll move back down anyway, so you'll still have hopefully the text. So if we take a look at question 2 that we're going to deal with, what we've studied so far is the equation g of x equal to 0. And what we want to do now is use analysis of the variations of g. So we need to compute the variations of g and deduce where g of x is negative. And it's not really clear from our analysis so far. I suppose despite the fact that we've sort of solved g of x equal to 0, we haven't paid that much attention to the sign of g. And we're going to do it through variation analysis. So this is going to be the opportunity to, review the different techniques that we have. So let's have a look at the variations of the function g. So the first thing, g is C infinite on R. Okay, we've seen that the hyperbolic sine and cosine are C infinite on R, I think. And this is just a sort of combination of the two. So that's the first thing that we can say, and it allows us to justify any differentiation we do. Does G have any parity properties?
Yes, it is even, because
Yeah.
the square of a function is even, and the hyperbolic cosine is even, and so.
Absolutely. Yeah, you're absolutely right on that. So if we take any x on R, and we take a look at g of minus x, and use the expression, so we should have sh squared of minus x minus 2sh of minus x. Okay, here, even though sh is odd, so you'll get sh of minus x equal to minus sh of x. And then when you square it, you'll just end up with sh squared of x, and ch of minus x is equal to ch of x. So that's equal to g of x. Okay, so the function g is even. And we can restrict our analysis to R plus. So we're going to take some x greater than 0 to do our analysis. So with this in mind, we can compute the variations by using a variation table. And at some point, we're going to use question 1 to complete our variation table as well. Now, if we take x in R plus, g of x, or g prime of x rather, is equal to sh squared of x minus 2ch of x prime. Okay. So what do you get when you derive this function here? I suppose the first step is you get a derivative of sh squared, and then you get minus 2 times the derivative of ch.
We get sh of x times ch of x plus sh of x times ch of x minus 2 sh of x.
Yeah, I think when you with the sum that you gave, you end up with the right formula. You should end up with 2 times sh of h ch of x minus 2 sh of x, which I think is exactly what was said. And so if you factorize this, you get 2 sh of x times ch of x minus 1. Okay, and this is the derivative of the function. And so what's important is that we manage to establish the sign of this derivative. Can you tell me anything about the sign of the different parts of this derivative?
2 times sh of x is always positive.
Yeah, someone else was about to say something, I think.
I was going to say that the term ch of x minus 1 is always positive since ch of x is superior to 1.
Exactly.
Well,
yeah.
It's in R plus.
Yeah, absolutely. So sh of x is positive on R plus. Okay, and ch of x minus 1, that's positive for any x on R. Okay, so if we combine the two, so for any x on R plus, combining these two properties, we get g prime of x positive. Okay, so that's going to help quite a bit with when it comes to establishing the set where I think g of x is smaller than 0, because as g prime is positive on R plus, the function is going to always be increasing. And if we manage to establish different values, we should be able to find basically where the function's positive and where it's negative. So what we get from this is a variation table. So for the values of x, we can restrict ourselves to R plus, so we can go from 0. We can take the value from question 1 where we know the function is equal to 0. Okay, we know that it's logarithm of 1 plus square root of 2 plus square root of 2 plus 2 square root of 2. The function is equal to 0, and you can probably see why we answered that question first now. We know that if we take g prime is positive on the whole of R plus. So it remains to just give some behavior for g. We've already got 2 things. We know that the function's increasing and it's equal to 0 at the point that's given. That's from question 1. And we could perhaps specify some values for the function. So if we compute g of 0, That's equal to sh squared of 0 minus 2 times ch of 0. And that's, if you take a look at what it is, that's equal to minus 2. This is 1, and this is 0. So here you've got minus 2. And then we can take a look at what happens to the function at plus infinity. One way of doing that is saying that for any x on R plus, g of x is equal to the expression that we used in the first question. So the one where we just have ch, and you'll see why it's nicer if you just have ch. So we have ch squared minus 2ch of x minus 1. Okay. That's equal to p of ch of x, where p of x is equal to x squared minus 2x minus 1. Okay, so g of x can be written as a composite function. So it's a polynomial applied to ch of x. And now we should be able to compute a limit. So if we take a look at plus infinity for p of x, what value does the polynomial go to at plus infinity? Or actually, that's a bit of a silly way of doing it. What value rather does ch of x go to at plus infinity?
Plus infinity.
Yeah, absolutely. And then if we take y to plus infinity and consider p of y, we'll get plus infinity. So if we use composite limits, we get limit when x goes to infinity of p ch of x, that's equal to plus infinity. So this limit here is plus infinity. So this is the variation table of our function. Is there anything that we can say now about whereabouts this function, so g, is negative?
G is negative between the two roots.
Yeah, g is negative. So if we just consider r plus, it will be negative here. And if we use the parity of the function, it will be negative between minus, or rather between logarithm of 1 plus blah, blah, blah with the minus sign and this logarithm term. So yeah, we can write all of this and it allows us to conclude on the question. So if we take, for any x on 0, logarithm of 1 plus square root of 2 plus square root of 2 plus 2 square root of 2, what's going to happen is that g of x is going to be negative. Okay, and by parity, what the parity tells you is just that if we take minus that logarithm term, you'll be negative 2. Okay, but what we can do is prove that minus this logarithm term is actually the second root that we came up with in question 1. If we attempt to do this, so if we take minus logarithm of 1 plus square root of 2 plus square root of 2 plus square root of 2, what we hope for all our calculations to be coherent is that this is equal to the second root of question 1. And so if we try and work with the logarithm function, we can write this as the logarithm of a fraction. Okay, that's the first step we could do. And we could try and simplify this expression. One way we could do that is as follows. So it's going to involve multiplying by both the top and the bottom by 1 plus square root of 2 minus square root of 2 plus square root of 2. And we end up with this term at the bottom. Okay, so this is the exact term for the exact expression of the second root. And we'd want the term that's beneath to reduce to 1, hopefully. And in fact, it does. So we could call, I guess we can call this A, and that B, that's A, that's B. So it's of the form A plus B, A minus B. And so if we take a look at what the denominator is equal to, we'll get 1 plus square root of 2 squared minus the root of 2 plus square root of 2 squared. So we can expand the first square. So we get 3 plus square root of 2 minus 2 minus square root of 2. And you see that it reduces to 1. And so what we get is that logarithm minus the logarithm of the point we are at is in fact equal to the second root of the function, so everything is coherent. So if we want to just conclude on the solution set to the initial question, so if we set E equals the values of x in R, which g of x is negative, okay, that's equal to the interval.
Just a small detail. I think that
Yeah.
all the way up there, and by parity, you have minus ln of 1 plus square root of 2 plus 2 plus 2 square root of
Oh, yeah.
And so that propagates the error like everywhere.
Okay, wait a minute. Oh, yeah, you're absolutely right. So here, is that what you mean? Here,
Yeah.
Here.
And the red too.
Oh, yeah. Okay, the problem, it just ended up double compensating itself. Yeah, that should be better. Yeah. Thanks. Okay, so E, if we take a look at it, it just gives us an interval, and it will go from minus logarithm 1 plus square root of 2 plus square root of 2 plus 2 square root of 2, all the way up to the same point without the minus. And we could equally, I'll write it the other way around, so that I'll put a minus there. So minus this square root logarithm of 1. That should be okay now. There. So it's a bit of a pain. A lot of the expressions are not very pleasant to deal with, but that's how you can find a set of values for which g is negative, despite the fact that g isn't a very nice function to start with. So I can leave that on the screen, and we can take a break now for 15 minutes, and then after the break I think we'll take a look at exercise 6. So we're going to study power functions. I'll just cut the microphone. We can get started again. We're going to tackle exercise 6. So if you have the exercise sheet in front of you, you can see that exercise 6 is quite a long exercise. And it's going to involve studying functions that are called power functions. So you know some power functions, polynomials, for example. So x squared, x cubed, x to the power 10. Some simple rational functions are power functions as well. So 1 over x writes as x to the power minus 1. 1 over x squared writes as x to the power minus 2, etc. So those are some simple power functions that you know. You also know the square root function, which you know writes as x to the power 1/2. And so in all of this exercise, we're going to work on power functions and define some new ones. So we're going to look at a to the power x. And we're also going to look at x to the power alpha, but when alpha is a real number. So if you come from abroad, if you studied abroad, you've possibly seen these things already. So it will be just, I suppose, just reviewing those things again. In France, normally this is the first time that we extend all of the power functions. And so we're going to work on all of this in the following hour. And so a bit like the hyperbolic functions, and we're going to prove all of these as part of the tutorial exercises, but you'll be able to use the results from now on. So what we do to define power functions is use the following form for x to the power y. Okay, we mentioned before that if you see something of the form x to the power y that you're not already familiar with, so for example, it's not x squared or something like that, your first sort of reflex should be to write it of the form exponential of y times logarithm of x. And the first thing that we're going to do before studying the functions as such is just prove some formulae here. So we've got 6 things to prove. That should be an and. How would you go about proving, for example, the different statements? Maybe this one to start with.
It's just an
Maybe
equality.
we could rewrite. Sorry, maybe we could rewrite it as e to the x. Sorry, e to the x ln of a. Wait, no, e to the
Almost, yeah.
a alpha log ln of x plus ln of
yeah.
no,
You're
sorry,
right.
I e to the
Don't
alpha
worry.
plus beta times
Yeah.
ln of x. Sorry.
Absolutely, yeah. You had the right idea. It's just getting it's confusing sometimes the order in which things are in the exponential, but you're absolutely right. So if we let xy in r squared, or r plus squared, I think is what we take here, and let alpha beta in r squared, then so x to the power alpha plus beta, that's equal to what we can use to prove the equality is this equality here. That's how the sort of x to the power y is defined. So that's the definition. So the definition of x to the power alpha plus beta is exponential alpha plus beta times logarithm of x. And then we can rewrite that, if we want to go a bit slowly, as exponential alpha logarithm of x plus beta logarithm of x. And then what can we use from there?
That is the same as e to the alpha ln of x times e to the beta ln of x.
Yeah, of course, we use the exponential function properties. So we get the following product. And then using the definition of x to the power alpha and x to the power beta, we reached a conclusion. So to prove all of these formulae, it's just a case of, how can I put it, of using the definition and then rewriting things with the properties of the exponential function. So now if we tackle x to the power alpha to the power beta, we get exponential alpha logarithm of x to the power beta. And so here, once again, we can use the exponential properties. So what does that mean for the exponential function? Or for using the exponential function, how can you deal with this?
We have b times alpha e to the b times alpha ln of x.
Exactly.
And so on.
Exactly. Yeah, so we just bring beta into the exponential and we reach the definition of x to the power alpha times beta. I think we'll do one last one of these, and the 3 others you can do at home because the method's always the same. So x to the power minus alpha, you get exponential minus alpha logarithm of x. But what property can you use then from over the logarithm or the exponential functions to rewrite this?
That's equal to e to the ln of 1 over x to the alpha.
Yeah, absolutely. Yeah, we could do that actually. And then we should get 1 over x to the power alpha. I'm going to put 3 dots here. There are basically no surprises with the 3 other equalities. So you can do those, I think, with absolutely no trouble at home. So try and do them at some point if you have time to look over chapter 6. But we won't spend any more time on this question here. I think you get the gist of this. So all this tells you is that all of the properties that you naturally sort of use with power functions, in a lot of cases that you already know of, you use all these properties without any problem. This is sort of a rigorous proof of such properties based on the definition of the power function. So x to the power y equal to exponential y logarithm of x. And now we've defined the exponential and logarithm function in class sort of properly, we can apply it to x to the power y. Now, with that in mind, the key part of this exercise involves studying 2 functions. The first one involves studying a to the power x. So for example, you could study the function f of x equal to 2 to the power x and want to know its behavior on R. And as you can see, the sort of different questions we're going to answer relative to fa of x, which is the function at hand, are really quite detailed. And so this gives you an idea of what you'd generally be asked relative to functions if you're asked to analyze them. So what we're going to consider here is a positive value a. So we take a in R plus star. We're going to define fa of x as follows. So it's going to map R to R, and it's going to map x to a to the power x. And the first step, as you can guess, is going to probably be rewriting things with the definition of the power function. So, and as part of the first question, we're asked to give the definition, continuity, and differentiability domains of FA. And maybe a first step to that is looking at what the function rewrites as. So how can we rewrite a to the power x with the exponential and logarithm function? So we've got a to the power x, and we've got the definition up here.
Exponential of x, logarithm of a.
Yep, absolutely. So it writes under a perhaps nicer form, exponential of x, logarithm of a, and you can probably see now why we needed a here to be an r plus star. Okay, it could be tempting, sorry, to take a negative number here, but that's not possible with this definition of power functions. So that's a more sort of analyzable expression. Can we give the definition, continuity, and differentiability domains of this now?
Yeah, we have a function x times ln of a, which is a number. So that's defined in R, and E is also in R. So we can say that f of a is defined in R.
Yeah, you're absolutely right. It's defined in R. Where would it be continuous and differentiable? Maybe one thing that to give you an
Also
idea
in
of what, yeah, exactly. An example of such a function that you can write: if a is equal to e of 2, then f of e2 of x is just exponential of 2x. Okay, logarithm of a here gives you logarithm of e of 2, so that will give you 2, and so you get exponential of 2x. So the important thing to bear in mind is that logarithm of a, although it seems like a strange expression, is just some constant. Okay, it's a constant that happens to write under the form logarithm of something. But this here is just an exponential function with a sort of strange constant. So what we have is that the domain of the function, the definition domain, is equal to the continuity domain, is equal to the differentiability domain, equal to R, as fa is the exponential function. Or an exponential function, I guess, rather. Now, the second question asks us to compute the derivative of fa of x. So we're going to compute the derivative on the differentiability domain, which is d of d. Okay, and that's r. And we want the derivative fa prime of x, which is the derivative of exponential x logarithm of a. So what is this derivative equal to?
Ln of a e to the x ln of a.
Exactly. That's equal to ln of a ex ln of a. And if you want to, you can identify that this is a to the power x. So it also writes as ln of a times a to the power x. So that's the expression of the derivative, and obviously this term here is easy to analyze going forward. It's easier than the one on the right hand side. So that's the derivative. The next thing that we want for this function is the limit of the function when x goes to infinity. So limit when x goes to infinity of fa of x. That's the limit when x goes to infinity, exponential x ln of a. So what can you say about this limit?
It depends on ln of a. If ln of a is positive, then it goes to plus d infinite. If it's negative, it goes to 0.
Absolutely. So it will go to plus infinity if ln of a is positive. So in particular, if a is greater than 1. If a is equal to 1, then ln of a is equal to 0. And so the function just remains constant in that case, and equal to 1. And it will go to 0 if a is smaller than 1, as in that case ln of a is negative, and you get exponential minus x roughly behavior wise. So that's the limit of a function. So from this limit, it becomes apparent that there's basically 3 different cases for the behavior of this function. And I think what's asked for in question D, in question D, we're going to give the variation table of FA. So in practice, we're going to draw 3 variation tables. And one thing that we can note is that the sign, so if we want the variation tables, notes that the sign of FA prime is equal to the sign of ln of a. Again, here we already gave 3 different cases depending on the values of logarithm of a, and we'll find the 3 different cases below. Okay. So the first possibility that's also written above is when a is smaller than 1. In that case, we have the following. So we can do the variation table on R. We have FA prime and FA. So what happens to the sign of FA prime when A is smaller than 1?
It's negative.
Yeah, absolutely, it's negative. And so we deduce that the function is decreasing. So it goes to 0 when x goes to infinity, as is written above here. And you can also prove that the limit when x goes to minus infinity of exponential x ln of a when a is smaller than 1 is equal to plus infinity. Okay, you've got x that's negative going towards minus infinity, and logarithm of a is negative. So the thing will go to plus infinity. So that's a first variation table, and you can see that the variation tables are quite simple to come up with. There's the function's monotonous. A second variation table we can draw, which is, I guess, even simpler, is when a is equal to 1. So in that case, what happens to the derivative and to the function in this case?
It is equal to 0.
The derivative is equal to 0. Yeah,
Yes.
and the function?
Is equal to 1.
Yeah, absolutely. So it's equal to 1, and so the limits in particular are equal to 1. So the second case is easy to draw. And then the third case is the case where a is greater than 1. Okay. And in that case, we're going to have the following behavior. So f prime is positive. The function is going to be increasing. We proved above that the limit's equal to plus infinity at plus infinity in this case. And at minus infinity, exponential of x logarithm of a will go to 0. Okay, the behavior of, in this case, is sort of the opposite of the behavior in the first case. Why do I keep getting that? Okay, so those are 3 different variation tables, and based on the 3 different variation tables, we should be able to plot the values of the function on R, or the sort of behavior of the function on R. So we can draw 3 graphs. I'll try and put them side by side because there's not much to put on them. So first case is the case where a is smaller than 1. If a is smaller than 1, we'll be able to compute and check that the value at 0 is equal to 1. And you've basically got the behavior of an exponential function. That's f of a, and that's the case where a is smaller than 1. When a is equal to 1, we'll get this. So if I put, so 1 is here, 1 is here again, and 0 and 0. In this case, the function is just a constant mapping. This is when a is equal to 1. Then finally, when a is greater than 1, we can draw a third graph, sorry. So we've got 0, 1. And again, this would be resemble an exponential function. There. So those are 3 graphs, and for any a in, what is it, R plus star, we can compute f a of 0 is equal to exponential 0 times logarithm of a, and that's always equal to 1, which justifies this point here being the same for all 3 graphs. Okay, so basically, when you have a function of the form a to the power x, you've got 3 possibilities. When a is equal to 1, you're constant and equal to 1. When a is below 1, you're basically like an exponential of a negative x. And when a is greater than 1, your behavior is like that of the exponential of a positive value x. So is the reasoning behind these 3 functions okay? It's fine. Okay. Okay, so if that's fine, we can turn to a slightly harder case. So we've done a to the power x. We can now do x to the power alpha. And as you can see, we're going to differentiate between 3 different cases. And we'll see that 2 of these cases are cases that you know of already. And one final case is the one that's going to take up more of our time. Okay, so going forward, we're going to consider the sort of opposite type function. We're going to consider x to the power alpha. So this is question 3, and we're going to let alpha in R, g alpha of x is going to be x to the power alpha. And we're going to distinguish 3 cases, and in 3 cases we're going to give the definition, continuity and differentiability domains of the function. So let's take a look at that. So what happens to these functions when we have alpha in n, so a positive integer? So if we take alpha in n, for example, alpha equal to 2, where is this function defined, continuous and differentiable? Where's the x squared mapping, continuous and defined and differentiable?
On R?
Yeah, absolutely. So if alpha is in n, let me just move that a bit. If alpha belongs to n, g alpha is a polynomial function. Is therefore C infinite on R. So d of g alpha is equal to d of c equal to d equal to R. So the function is defined, continuous and differentiable in the same places. Okay, so that allows us to deal with one case. Now, the second case that we consider is alpha in z. Okay, so that includes the negative integers. And in particular, we're going to look at what happens when alpha is negative. So what happens in this case? So it's, for example, x to the power minus 1. Where is 1 over x defined?
On R star.
Yeah, absolutely. So 1 over x is defined on R star, and that generalizes to x to the power alpha with alpha negative. Basically, in this case, g alpha is a rational fraction. And is C infinite on R, from which we remove 0, because the only pole of unique pole 0. So the definition domain of the function is equal to the continuity domain equals the differentiability domain, and it's R, from which we remove 0. So that's the second case. And the final case is going to be the one that we're going to spend more time analysing, because as you can see in these two first cases. We can give the definition domains and continuity and differentiability domains, but we also sort of know what the objects are. So they're either a polynomial function or a rational fraction, and we already know properties of these two objects. So the final case, where we're first going to look at sort of definition domains, is alpha in R from which you remove Z. Okay. How can we rewrite x to the power alpha in that case? Okay, in that case,
Exponential of alpha log of x.
Yeah, absolutely. We need, in this case, we need to use the definition and obtain x to the power alpha equal to exponential of alpha logarithm of x. What you can note then is that this is only defined on R plus star. Okay, but what we now want to do is find out where the function is also continuous and differentiable. Now, and what we can note to do this is that we're basically doing a composition of two functions. So we've got the exponential function, and we apply the exponential function to the logarithm function. So we can note that ln is C infinite on R plus star. The exponential is C infinite on R. So G alpha is C infinite on R plus star. So that's the first thing that we can note. One thing that we can do now is study the function a little bit more at 0. And that will allow us to come up with a definition, continuity, and differentiability domain. So we're going to study what goes on at 0. So for any x greater than 0, we can say that G alpha of x is equal to exponential alpha logarithm of x. Okay, that's using the definition that's written above here. So if we take the limit when x goes to 0 of G alpha of x, that's equal to two different values depending on the value of alpha. Basically, if alpha is positive, we'll get the limit value at 0 equal to 0. That's because logarithm of x at 0 goes to minus infinity, and plus infinity if alpha is negative. And I suppose you could wonder why we even mention this limit, because we've already established that G alpha is C infinite on R plus star. What we're going to do here is perform something called a continuous extension of the function. So what we can see through this limit is that if alpha is negative, the limit of the function is plus infinity. So there's no way that this function can be well defined at 0. But in the case where alpha is positive, which corresponds, for example, to the square root function, and you know that the square root function is defined at 0, despite the fact that all of this reasoning so far only gives us defined on sort of R plus star, so not at 0. And so we're going to work towards showing that it is defined at 0. Okay, what we can exclude from this is the case where alpha is negative. So if alpha is negative, of G is equal to D of C, so continuity domain, differentiability domain, and that's R plus star. If alpha is positive, we can perform what's called a continuous extension. So we set G alpha of 0 equal to 0. Okay, that's something that we define. And we set G alpha of x equal to x exponential of alpha logarithm of x for x strictly positive. Okay, and we know that as limit when x goes to 0 of G alpha of x is equal to 0 is equal to G alpha of 0, the resulting function is continuous. It will be continuous at 0. And we sort of extend the function by adding the sort of limit point to the edge of the function, despite the fact that with the initial expression, it doesn't seem quite possible. So what we get from this is dg of alpha is equal to dc, so continuity domain, and that's equal to R plus. Now, in the same way that we've looked at the continuity at 0, we can have a look at the differentiability at 0, okay, of this function. And we'll do it in the case where alpha is positive, okay? When alpha is positive, we've added sort of 0 onto the end. That's coherent with the square root function. And we're going to have a look and see if we can do anything related to differentiability. And we'll see that sometimes we can. So what about differentiability at 0? So if we want to have a look at differentiability at 0, we're going to have a look at the difference quotient at 0. And so we're going to have a look at G alpha of x minus G alpha of 0 divided by x minus 0. Now we've defined G alpha of 0 here to be equal to 0. So that gives us G alpha of x divided by x. Now if we use the definition of G alpha of x, how can we rewrite this fraction? Okay, if you just replace G alpha of x by its expression, it's x to the power alpha. You divide it by x, and so you get x to the power alpha minus 1. And so if we take the limit when x goes to 0 of G alpha of x minus G alpha of 0 divided by x minus 0, we'll get, using this, we'll get 0 if alpha minus 1 is positive, and plus infinity if alpha minus 1 is strictly negative. So we deduce that when alpha minus 1 positive, i.e. Alpha greater than 1, G alpha is differentiable at 0. and it is not differentiable at 0 when alpha minus 1 negative, i.e. alpha smaller than 1. So we've got two cases now for the different domains. So finally, if alpha is greater than 1, okay, we have the definition domain equals the continuity domain equal to the differentiability domain equal to R plus. Okay, you can go to 0 for continuity and differentiability. And if 0 is smaller than alpha, smaller than 1, you have two things. The definition continuity domain will be R plus, and the differentiability domain will be R plus star. So we've got three different settings to consider for all of the for the function x to the power alpha when you consider a general value alpha. And so now we're going to basically analyze the function x to the power alpha in this general case. So basically not in the case where it's a polynomial or a rational function. And we're going to see how this function behaves. And here, as we've got three different cases, so we've got, where is it? Alpha negative, that's the first case. Alpha between 0 and 1, and alpha greater than 1. That will give us three different graphs, much in the same way that earlier here for values of a, we had three different graphs and three different sort of behaviors. And so we're going to perform the analysis of the function with that in mind. So I suppose what I've done here actually includes sort of a and b in one, because I dealt with continuity and differentiability at 0 in here. So in question A in one go. So what we're going to do next is compute the derivative of the function. So let's take a look at question C. So you want to consider x on R plus star. That's where the function's defined in a general case. Okay, then g alpha of x is equal to exponential alpha logarithm of x. Okay, and what's the derivative of this function when it's under this first form? Okay, have you got bad internet, or are you lost, or are you doing something else?
I'm a little bit just following and not really doing this exercise.
Okay.
Of just following the correction and understanding that way.
Okay, is it too quick? You need to tell me if I'm going through things too quickly, or...
No, I wouldn't say it's too fast.
Okay, it's probably just a lot to... yeah.
Getting into it. I don't know. I just...
No, don't worry. Yeah, and it's probably a lot. This is a bunch of new functions, so there's a lot of material in one go, so no, it's probably quite normal. Yeah, what we can do here is compute the derivative of this function using tools that we've learned so far. So if we take this composite function, forgetting about the fact that x is an R plus star, and we want to derive it, we can do it as follows. So it's a g of f of x, basically, So it will be g will be the exponential, f of x will be alpha logarithm of x. And so if you derive it, you'll have f prime of x. So that's alpha over x, as alpha logarithm prime is alpha over x. And then you take the derivative of g, which is the derivative of the exponential, which is the exponential, and apply it to f. So we get this function here. And if we look at what it sort of rewrites as, so you've got a constant alpha divided by x times x to the power alpha. And so we get alpha x to the power alpha minus 1. And so this probably reminds you of derivatives of, for example, polynomials, or you know, for example, that if you derive x to the power 4, then you'll get 4x cubed. In fact, you know that if you derive the square root function, so x to the power 1/2, you get 1 over square root of x. So that's actually 1/2 x minus 1/2. Okay, and both of these settings fall into this sort of case. So x to the power alpha prime is alpha x to the power, is alpha x to the power alpha minus 1. And it includes all of the derivatives you know so far for power functions, and generalizes to the case where alpha here is a real number that's positive. So that's the derivative. But if you take a look at what I've just written above, there's a specific case. So it's the case where alpha is greater than 1, where you can differentiate the function at 0. Okay, so if alpha is greater than, not x, alpha is greater than 1, we saw above that the function can be derived or derived at 0. Indeed, limit when x goes to 0 of g alpha of x minus g alpha of 0 divided by x minus 0. In this case, I've proven it here. That gives us 0. Okay, so we set g alpha prime of 0 equals 0, and that's equal to alpha times 0 times alpha minus 1. So if we take the limit of the difference quotient, we get 0, which suggests that the function is differentiable at 0. And 0 is actually an extension of the derivative that we get here. And so this sort of setting, this extra setting where alpha is greater than 1, and you can differentiate your function on R plus, gives you a formula that's that works even in this extra case. So what we get, that's well defined if alpha is greater than 1. And we get for any x on the differentiability domain, okay, that will be equal to r plus star in most cases, and r plus when alpha is equal to 1 or greater than 1, sorry. G alpha prime of x is equal to alpha x alpha minus 1. And so this here, r plus star, so it's r plus if alpha greater than 1, r plus star otherwise. And there's one formula for all of those cases. Okay, so that's the derivative. And we can see that the sign of the derivative here, as x is positive, the sign of the derivative will be given by the value of x. So it'll either be positive or negative, and the variations of the function will sort of be deduced from that. But before we give the variations of the function, I think there's a limit to compute. So it's the limit at plus infinity of this new function. So let's have a look. We want the limit when x goes to infinity of g alpha of x. If we use the definition of the function, it's the limit when x goes to infinity of exponential alpha logarithm of x. Okay, the logarithm function at plus infinity goes to plus infinity. And so the value of this limit will depend on the sign of alpha. So you get 0 if alpha is negative, and plus infinity if alpha is positive. So that's a result related to the limit. The case where alpha is strictly positive is coherent with what we know for the square root function, which is quite reassuring. Now, following on from this, let's see what the next question is. Yeah, so following on from this, we're going to basically graph the functions. So we're going to answer some sort of standard questions. We're going to give the variation table of g of alpha, and then you can see here that we're going to give an example of convexity and concavity. And as you can see, the sort of it's explicitly asked, and it will help us draw the graph, I think. So let's first have a look at the variation table of the function. So we're going to have 3 variation tables, depending on the values of alpha. So we have 3 cases. We're going to have alpha strictly negative, alpha between 0 and 1, and alpha greater than 1. Okay, so if we consider the case where alpha is strictly negative, we have a function that's only defined on r plus star. Okay, so the function doesn't have any sort of specific value at 0. And we have the following variation table. So we're going to take values between 0 and plus infinity. We have g alpha prime in this case. If you have a look at the expression above, where was it? It's here. As alpha is negative, that will be negative. And so the function will be decreasing. Like this. And I think we proved above that the function goes to 0 at plus infinity. We can also, I guess, have a look at the limit at 0. So the limit when x goes to 0 of exponential, what was it? X alpha logarithm of x. If alpha is negative, logarithm of x at plus infinity goes to minus infinity. And so times the positive value will go to plus infinity, and the exponential goes to plus infinity then. And so the function basically goes down from plus infinity without being defined at 0, and then decreases all the way down to 0 at plus infinity. So that's first case. And then we've got 2 other cases. Actually, we're good for the, no, we'll keep the 2 different cases here. So what's going to happen in the 2 other cases is that the variations of the function, as they're given by the sign of alpha, which is positive, are going to be the same, but we'll see that the behavior of the function isn't quite the same. But in the first case, we have this. So we go to plus infinity at plus infinity. The function's equal to 0 at 0, and we increase. And one thing to note is that in this case, we computed the difference quotient at 0 above, and it's equal to plus infinity. So in this case, the difference quotient at 0 is equal to goes to plus infinity. So the function has a vertical tangent at 0, and as it has a vertical tangent, it's not differentiable. And if alpha is greater than 1, we'll have the same variations, but there will be a well-defined differential at 0. So in this case, the differentiable at 0 okay. So that's it regarding the variation tables. And the final thing that we're going to do regarding these functions now, before we graph them, is give the convexity and or concavity of these two functions. So let's take a look at this. So how can we find whether a function's convex or concave? Can you remember from
by taking the
class
second
earlier on?
derivative?
Absolutely, yeah. So we can take the second derivative, and we need to be in a setting where the second derivative exists. So to be safe, we're going to restrict ourselves to r plus star, which is where all the functions are C infinite. And we're going to have a look at the second derivative of exponential, alpha logarithm of x. So that's our function, and we're going to want to take the second derivative of it.
I have a question.
Yeah.
Regarding functions that are not necessarily differentiable twice, is there an easy applicable method for the other way to define if it's convex or concave, or is it not?
Oh, yeah, that's a very good question. No, you're generally a bit stuck, basically. If your function's not twice differentiable, there's it gets complicated to find convexity and concavity. I suppose sometimes you can still study the variations of f prime, even if it's not differentiable. For example, imagine this function exists. Imagine you've got a function whose derivative is this strange function, so it's a step function. And there are sort of parts here where the function is not defined, but it's still basically increasing on r, or r plus, for example. Then your function is still going to be convex, I think, because your second derivative is increasing. Oh, sorry, your first derivative is non-decreasing. But you have to really look at the behavior of the first derivative. And in most of the cases that you'll be in, your function will be twice differentiable if you have to deal with convexity or concavity.
Okay, thank you.
You're welcome. So we're going to look at the second derivative of this, and we have the first derivative somewhere above. So let me find that. It's here. So we have the second derivative of this thing. So that's the first derivative, and we want to derive this again. And so you've got the product of two terms. So the first thing we can do is derive the first term. So we should get minus alpha over x squared times exponential alpha logarithm of x. Yeah. And in the second case, we're going to derive this term and multiply the derivative by that. We should get alpha squared, x squared, exponential of alpha logarithm of x. And so we can factorize this a bit. So we've got alpha, factor of alpha minus 1 times exponential alpha logarithm of x divided by x squared. Okay, so this is the second derivative. And what we can see here is that on the right hand side, we have a term that's positive. Okay, the exponential function is always positive and x squared is always positive. And so the sign of this function is going to be given by the sign of alpha maps to alpha minus 1. Bearing in mind that alpha is valued somewhere on R, I think. So it can either be negative or stuck between 0 and 1 or greater than 1. So what we're going to do is have a look at the sign of alpha, alpha minus 1. So that's what's key to the sign of our second derivative. So you can do a sign table if you want to find the sign. And there are other ways of doing it, but this one will work. So if we go from minus infinity to 0 to 1 to plus infinity, alpha will be negative and then positive. Alpha minus 1 will be negative, negative here and then positive. And so the resulting function will be positive, negative, positive. Okay, so alpha minus 1 is is negative for alpha between 0 and 1 and positive otherwise. So what does that tell us about the convexity or concavity of our functions?
It is convex between minus infinity and 0 and between 1 and plus infinity, and concave between 0 and 1.
Exactly. So therefore G alpha is convex for alpha in R from which we remove 0, 1. Maybe I should even do it convex on R, or on R plus star rather. Okay, and it will be concave on R plus star for alpha in 0, 1. Now, what setting does the square root function fall into?
Where G alpha of x is concave.
Exactly, yeah. So this setting here includes a square root function. And so a good idea to sort of be able to visualize the behavior of concave functions and the behavior of in this setting, so alpha between 0 and 1, is to bear in mind the behavior of the square root function. So that gives us convexity or concavity, and it will allow us to conclude on the graphs. So it's question G. Okay. I'm going to be able to give the graphs of the function. And as you can imagine, we're going to give 3 graphs. For alpha smaller than 1, alpha smaller than 0, alpha between 0 and 1, and alpha greater than 1. So if we take, first of all, the case where alpha is smaller than 0, we only need to plot the function on the positive part of R, so only part of the graph. If we take a look at the variation table, we can see that the function decreases from from plus infinity to 0, and it's a convex function. In fact, the behavior is something like this. So at 1, the function is equal to 1, okay, because 1 to the power alpha, even if alpha is negative, it gives you 1. And so the behavior of the function is something like this, but I'll shift 1 to give me a chance of a nicer drawing. So put 1 here. I'll get there. Something like this. So it goes to 0 plus infinity, and that's the case alpha is negative. And you can see that it's convex because it's above all of its tangents. So if you draw a tangent to the curve that I've just drawn at 1, for example, you get something like this. All of its tangents are to the left-hand side of the function. So that's the case where alpha is smaller than 0. Now, if we take a look at what happens when alpha ends up between 0 and 1, you know that function increases. You know that it goes from 0, it goes through 1 at 1, and then it goes to plus infinity. But you also know that it's concave, and you know that it has a vertical tangent at 0, very like the square root function. And so the behavior, if I can get it, is something like this. Very roughly, it increases to 0, increases to plus infinity quite slowly. You have a vertical tangent here, okay, and in general, if you look at its curvature, if you have a better drawn function than this, you'll be able to see that all of its tangents are above the curve as it's concave. So that's what happens when 0 is smaller than alpha, which in turn is smaller than 1. And the final setting is where alpha is greater than 1. So again, I can place 1, 0, and 1. Alpha greater than 1. So we know that the function is increasing from 0 to plus infinity here as well, but we also know that it's differentiable at 0 with a derivative that's equal to 0. So the tangent is basically a horizontal tangent at 0. And the behavior, if you take a look, will be something like this. And so you're going to be above all your tangents. And so that's roughly what happens for alpha greater than 1. So in each of these cases in red, it's g of alpha. Okay, and you can see that the behavior that happens with alpha is quite subtle. So some rough examples. An example of this is square root of x. An example of this is x squared. Of course, x squared is then defined on the whole of R, the whole of R, so even on R minus, but you can sort of visualize the behavior of this as it's roughly x squared, and the behavior of this is roughly 1 over x. Okay, that will allow you to try and visualize the behavior. Okay, and that finishes this exercise on power functions. So, do you have any questions related to what we've just done?
No, not really.
No?
No.
Okay. Yeah, it's quite a long exercise. Everything that we've proven you can then reuse, a bit like the stuff on hyperbolic trig functions. And yeah, these types of functions, you'll sort of encounter them quite a bit, I think, over the next few months and few years. They're quite useful functions, but we've just extended what you know on some power functions to the sort of more general case. So that means we've done exercise 6. We've done that one, we've done that one. Yeah, we've almost done, I think, the exercises related to chapter 6 now. So further on in the week, we'll finish these 3 exercises related to basically inequalities, a bit like the inequalities we mentioned earlier on today. And then what we'll do after that is that we'll apply chapter 6 to an analysis of sequences. So you defined, I think, sequences in Math 0, and we're going to build on what you know about sequences using the tools that we now have for function analysis, and we'll see that we can actually go quite far with sequences using these tools. But that's it for today. So if you have any questions, don't hesitate, but if not, we can stop there for today.
I don't have any questions.
Okay. Have a good evening.
Thank you. Goodbye.
Bye-bye.
Thank you. Bye.
Bye.